Welcome students to the fifth and final lecture on mathematical reasoning. As I said in the previous class, I will be solving several problems, so that the concepts of logical reasoning gets clear. In the last class, I have shown associativity of AND. If you remember, associativity, we have shown that P and Q and R is same as P and Q and R. And I wanted you to work upon associativity of OR. So, what about OR? That is P or Q or R is equivalent to P or Q or R. So, that is the question. I am sure many of you have tried, but let me do it in this lecture. So, we will do it via truth table. So, we have three variables P, Q and R, and we know that their truth values will be of the following 8 combinations. If you watch the order in which I am writing, you will understand that I am doing it in a systematic way. I am fixing the value of P, then for that there are 2 values for Q, and then for each one of them there are 2 values for R. So, accordingly, I am making it is F T T, F T F, F F T, and finally F F F. So, these are the 8 possible combinations of the truth values for P, Q and R. What we need to show? We need to show whether P or Q or R is equivalent to P or Q or R. So, let us first find out what is the truth value for P or Q. So, since P is T and Q is T, in this row P or Q is T. Similarly, T T, therefore, this is T, T F, this is also T, T F, this is also T. We know that since P is T, irrespective of the truth value of Q, it is going to be T. Now, F and T is also going to be T, F and T is also going to be T, F F is F and F F is F. Therefore, P or Q or R. Now, what we will do? We will OR between R and P or Q. So, here it is T T, therefore, T, T F, this is also T, T T, it is T, F T, again T, T T, T. Now, F or T, T, T F, T, F F is F. So, this is the only point where P or Q or R becomes false. Now, we look at from the other side. So, let us compute Q or R. Q or R, we will be ORing between the values along these two columns. So, Q and R is T, 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 F, T, 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 F. Now, we are ORing this with P. So, P or Q or R, therefore, is I am now ORing between this column and this column. T or T is T, T or T is T, T or T is T, T or F again T, F and A for T is T, A for T is T, A for F, A for T is T and A for F is F. Now, if we compare this column and this column, we find that they have the same truth values in all the rows. That is, for all possible combinations of P, Q and R, the truth values of P or Q or R and P or Q or R are the same, or in other words, we can say that this is true, that is, they have the same truth values. Therefore, in effect, we say that OR is associative. What about then P or Q and R? If we write the two symbols like this, then it is clear that there is an ambiguity. It may have two interpretations. It is P or Q and R, P or Q and R, right? So, we need to check if these two have the same meaning. In a similar way, what about P and Q or R? As before, it may have two meaning, P and Q or R, or P and Q or R. Which one of them we should take, or more importantly, we should check whether they are equivalent or not. To illustrate that, I will take a small example. Consider this following table. Suppose there are 5 students A, B, C, D, E, and there are 3 subjects: computer science, mathematics and statistics. In the table, we have given values G and B. G stands for good and B stands for bad. Therefore, we can see that A is good in all the 3 subjects, B is good in computer and maths, but bad in statistics, C is good only in math, but bad in both computer science and statistics, D is bad in computer and maths, but good in statistics, and E is bad in all the 5 subjects. So, we will see which of the 5 students satisfy this formula. We will get an idea, therefore, whether the expressions that I have given P and Q or R is equivalent to P and Q or R are not, or in a similar way, if P or Q and R is same as P or Q and R, where by P we mean good in computer science, Q good in maths, R good in statistics, and of course, not P implies bad in computer science, and like that. Okay? So, let us start. So, P and Q means who is good in both computer science and math, P and Q. So, both of them have to be true. So, we can write P and Q, the truth set is A, comma B. B also is included because it is good in both. Or R. What is R? R is good in statistics. So, who are the persons there? A and D. Therefore, the truth set for P and Q or R means anybody who is good in both P and Q or anybody who is good in statistics. Therefore, we get the union of this set, which is going to be A, B, D. In a similar way, let us look at P and Q or R. That means somebody who is good in computer science and who is good in either one or both of mathematics and statistics. So, because it is and, we have to find out the truth set for P, we have to find out the truth set for Q or R, and because it is and, we have to find the intersection of that one, right? Somebody who is good in computer science and somebody who is good in one of these. So, P is satisfied by A, comma B intersected with Q or R. That means somebody who is good either in maths or in stat or both. Therefore, we get A, we get B, we get C, we get D, and that is it. Because all these four is either good in math or good in stat. Therefore, what is going to be the intersection? The intersection is A, comma B. Intersection is A, comma B. P or Q and R. So, P again the truth value is A, comma B, and because it is OR, we will have to take a union with Q and R. That means, all those who are good in both math and stat. So, which are the students who are good in both math and stat? Only A. Only A is good in both math and stat. Therefore, this is going to be only A, B. On the other hand, if we look at P or Q and R, then by the similar logic, P or Q is going to give me A, comma B, comma C, and because it is an intersection, R you will be given by A and D, and therefore, we get the intersection to be A. So, what does it tell us? It tells us that P or Q and R and P or Q, then AND with that, have two different truth sets. In a similar way, we can find that P and Q or R and P and Q or R have two different truth sets. So, this example tells us that P and Q or R is not equivalent to P and Q or R. Similarly, P or Q and R is not equivalent to P or Q and R. Therefore, the question comes, how do we simplify this? Right? This comes by the distributive law. It says that P and Q or R is equal to P and Q or P and R. Similarly, P or Q and R is equal to P or Q and P or R. Okay? We will prove it using truth table. So, these are the distributive law. Let me do the first one first. We were showing P and Q or R is equivalent to P and Q or P and R. So, as before, we will take the truth values and by now you are familiar with the order. And finally, FFT and FFF. So, what is Q or R? We are now ordering between these two columns. So, it is giving me T, 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 F, T, T, T and F. Therefore, P and Q or R is giving me, I am now doing the AND operation between column P and column Q or R. Therefore, T and T is T, T and T is T, T and T is T, T and F is F, F and T is F, F and T is F, F and T is F, and F and F is F. What about P and R, or say P and Q? Here I will do P and Q, then I will do P and R, and then I will do the OR between them. Right? So, P and Q, I am performing the OR operation between these two columns. So, it is T, T, F, 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 F and F, right, because P and Q has to be true when both of them are true. So, we get these two to be true and all are false. P and R similarly is true here, false here, true here, false here, false here, false, false and false. So, the last task is to find the OR between these two columns, so that I can get P and Q or P and R. So, when I am ORing, it is going to be true when any one of them is true. So, true, 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 false, 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 false and false. Now, let us look at this column and this column. It is T T, T T, T T, F F, F F, F F, F F, F F. We see that for all possible arrangements of truth values between P, Q and R, we find that these two expressions P and Q or R and P and Q or P and R having the same truth values, right. So, what does it tell us? It tells us that P and Q or R is equivalent to P and Q or P and R. Okay? I leave it as an exercise for you to show that the other one, that is P or Q and R, is equivalent to P or Q and P or R. Okay, students. Now, let me take up another problem. This is the problem. Which of the following are contradictions? What do you mean by a contradiction? A mathematical statement is said to be a contradiction if it is false for each combination of the truth values of the component variables. In this case, we have P and Q, or in this case it is singleton P, which is the variable. So, we have to see if against different arrangements of values of truth values for P and Q, whether how many of them are giving F for all possible combinations. So, I write down the problems again. P and Q or not P, B, P implies not P, C, not of P and not P implies P or not P, and D, P implies Q implies P. Okay. So, let us see the first one. P and Q, now we have only 4 possibilities of their arrangements of truth values: T T, T F, F T and F F. So, not P is opposite of P, therefore, this is going to be F F T T, and P and Q is going to be true, false, false and false. Therefore, not P and P and Q is going to be the AND operation between these two columns, and we can find that in each one of them at least one of the two values is F. So, this is F, this is F, this is F, this is F. Therefore, we can find that P and Q and not P is a contradiction. You can even easily find out that P and Q means both P and Q have to be true, and its conjunction with not P means if P is true, not P is false. Therefore, you cannot get all three of them to be. When you are conjunction of these, you can never get a truth value to be true. It has to be always false, because P and not P cannot simultaneously be true in the propositional logic. Okay. What about this P implies not P? We have P and not P, two false, false, true, and P implies not P, true implies false is false, and false implies true is true. Therefore, P implies not P is not a contradiction. Because P can take values T and F, corresponding value is for not P is F and T, and from the table of implications we know that true implies false is false, but false implies true is true. Therefore, it is not a contradiction. Now, let us look at the third one, not of P and not P implies P or not P. Okay. How to do that? We know that P and not P is false all the time. And P or not P is a tautology which is true all the time, right? Because it is a tautology, as either P or not P, one of them will have to be true. Therefore, P or not P will always be true. Therefore, the whole thing boils down to not of false implies true, and we know that false implies true is true. Therefore, this is equivalent to not of true, which is equal to false. Therefore, this is a contradiction. Finally, we look at the fourth problem, which is P implies Q implies P. How to do it? Again, we do it in the following way. We draw the truth values for P Q, T T, T F, F T and F F. Now, we look at Q implies P. How does it look like? True implies true. Which is true? False implies true is true. True implies false is false, and false implies false is true. Therefore, what is going to be? P implies Q implies P. It is true implies true is true. True implies true is true. F implies F is true, and F implies tree is true. Therefore, it is not at all a contradiction, rather it is a tautology. All right. Now, I explain some interesting relationships coming out of P implies Q. What is the converse of it? The converse of it is that Q implies P. What is the inverse of it? Negation of P implies negation of Q, and contrapositive is negation of Q implies negation of P. This appeared to be little bit of abstract, but when I explain it with some real life example, it will be clear. Suppose P is the sky is cloudy. And Q is I take an umbrella. Therefore, P implies Q. What does it stand for? If the sky is cloudy, then I take an umbrella. What does it mean? The converse is Q implies P, right? So, the given statement is if the sky is cloudy, then I take an umbrella. It converse is that if I take an umbrella, that implies the sky is cloudy. Is it always true? Can we infer like that? That if I am taking an umbrella, that means it is cloudy? We can't infer the sky is cloudy. Why? Because I may take umbrella on other situations also, e.g. on a sunny day. So, I may take umbrella on a sunny day also. Therefore, just because I am carrying an umbrella or just because Q is true, it does not imply the sky is cloudy. or in other words, Q does not necessarily imply that P is also true. What about inverse? P implies Q, its inverse is not P implies not Q. Or in other words, if the sky is cloudy, implies, or say then I take an umbrella. Does it mean that if the sky is does it mean that if the sky is not cloudy, I don't take umbrella? No, again that is not correct, because I may take umbrella on a sunny day, right? Therefore, this is also not true. So, when it was converse, we are talking about whether me carrying an umbrella means it is cloudy. That is not true. Similarly, if the sky is not cloudy, that means that I don't take an umbrella. That is also not true. Therefore, what we can infer from P inverse P implies Q? Contrapositive. Let us look at it. Contrapositive means not Q implies not P. Therefore, what is not Q? Not Q is that I don't take umbrella, and not P means the sky is not cloudy. Therefore, if I am not carrying an umbrella, it is clear that the sky is not cloudy. It may be sunny, it may not be sunny, but this statement is definitely correct, because if the sky is cloudy, I would have taken an umbrella. So, the contrapositive can be inferred from the implication. So, this is a very interesting observation, that if P implies Q is true, P implies Q, then not Q implies not of P, or negation of Q implies negation of P. Let me give you another example. Suppose P is the statement ABCD is a square. Q is the statement ABCD has all sides equal. We know that P implies Q. What is going to be its converse? So, P implies Q. So, what is going to be its converse? Q implies P. which means if ABCD has all sides equal, then ABCD is a square. We know that rhombus does not fit, right. Rhombus may be the case, so this is not always correct. Inverse, not P implies not Q. If ABCD is not a square, implies ABCD does not have all sides equal. Again, that is not correct because of the same rhombus. Rhombus is not a square, but it does not imply that it does not have all the sides equal. But again, what is contrapositive? Not Q implies not P. That means, if ABCD does not have all the sides equal, then ABCD is not a square, and we know that that is true. If all the sides are not equal, it cannot be a square. So, simple logic helps us to verify this contrapositiveness, and we can see that converse and inverse need not necessarily hold from the statement Q implies P. Now, let us look at if P and Q are equivalent. Now, let us look at a simple example. What is the converse of the contrapositive of P implies not Q? This can be part of an MCQ, and you have been given different options, and you have to find out the converse of the contrapositive of P implies not Q. Since P implies not Q, its contrapositive is Q implies not P, right? Q implies not P, because if P implies Q, its contrapositive was not Q implies not P. Here not Q and having another not here. So, negation of Q is giving us Q. Therefore, Q implies not P. What is the converse of that one? The converse is Q implies P. So, the converse of P implies Q P implies Q, the converse is Q implies P. Therefore, what is the converse of Q implies not P? Its converse is not P implies Q. Now, let us look at some example. Say, consider three statements. A is a rectangle, Q, A has all the sides equal, and R is A is a square. We know that P and Q implies R. Because if A is a rectangle and A has all the sides equal, then together they imply that A is a square. What are the converse and contrapositive and inverse of this? So, our problem is find converse, inverse and contrapositive. So, we have P and Q implies R. We know that if P implies Q, then converse is Q implies P. Therefore, its converse is R implies P and Q. That is, if A is a square, then A is a rectangle having all the sides equal. Which is true. If A is a square, then A is a rectangle having all the sides equal. Therefore, if P, in this case we find that if P and Q implies R is true, then converse is also true. What about the inverse? Inverse is not P and Q implies not R. That is, now we can simplify not P and Q is not P or not R, not Q implies not R. Not P means A is not a rectangle or not Q is A does not have all the sides equal implies A is not a square. Which is correct? If A is not a rectangle, then A is not a square. If A does not have all the sides equal, then A is not a square. Therefore, inverse is also true. What is the contrapositive? P and Q implies R. The contrapositive is not R implies not of P and Q, that is not R implies not P or not Q. That means, if A is not a square, then A is not a rectangle or A does not have all the sides equal. Therefore, with respect to this example, we find that the contrapositive is true, the converse is true, and also the inverse is true. This is possible because the original statement P implies Q is equivalent to Q implies P. Therefore, P and Q are equivalent. We can get different truth values or different types of result. Now, let me stop with the last example. The last example is, consider the statement if x plus 3 is equal to 5, then x is equal to 2. If x plus 3 is equal to 5, then x is equal to 2. What is the converse? If x is equal to 2, then x plus 3 is equal to 5. What is the inverse of it? If x plus 3 is not equal to 5, then x not equal to 2. And what is the contrapositive? It says that if x not equal to 2, x not equal to 2 implies x plus 3 not equal to 5. So, these simple examples help us to understand the significance of contrapositive, converse and inverse. Okay, students, with that I conclude my series of lectures on mathematical reasoning. It is a very interesting topic. In the syllabus of the JEE Mains, we just work with two valued logics, that is, each logical statement have only one of the two possible values, either true or false. When you grow up and study mathematical logic in a deeper way, you will find different other modes of reasoning with multi-valued truth tables. Okay? Thank you so much.